is we will briefly talk about BFS, which is not going to take much time. My reading is that BFS should not take more than 15-20 minutes to understand. So we will do breadth first search because you have already seen depth first search, and this is just an extension. In fact, it's the same code, same everything. Only thing is, instead of using stack, which we used the last time, and that's why I made you write the code using a stack. So instead of using stack, we replace the stack with a queue, and you go from depth first search. So you have a stack here, and you have a queue here. So this becomes BFS. Everything else of the code remains same, but obviously this is a very powerful algorithm, especially if you want to do a level order traversal or something like that. This is very useful and very strong to use. And so let's talk about how the BFS or Dfs works. Okay, we are spreading the screen, no? You have to check, Baba. Okay, we will now start sharing the screen. So here we go. Now, okay. So I'll walk through the code, and it's pretty easy. If you understand even a little bit about programming, you will be able to do it. Okay. Yeah. We forgot to share the screen. Now we are fine. Okay. Now we'll walk through the code. Okay. So just to step back, DFS uses a stack, BFS uses a queue, and it goes breadth first, and this goes depth first. So if you take a graph, okay, let's take a notional graph just to illustrate the idea. Okay, let's take just some kind of a graph. No, there is some graph in the
here on the main. Can we use this main?
Okay. So here is a graph, and which is going to be done in this code. Sorry. So this graph. Let's try and draw this graph. So there is an edge from 0 to 1. There is an edge from 0 to 2 also. Then there is an edge from 1 to 2. And there is an edge from 2 to 0. Oh, sorry. 2 to 0. Okay. Some 2 to 3. 3. And from 3 to 3, there is a self loop. Okay. So this is the graph, okay, which we have talked about, which is the graph which we will create. Sorry. Okay, let me clear up this up. So 0 to 1, 0 to 2, 1 to 2, okay, 2 to 0, 2 to 3, 3 to itself. Okay. So this is the graph which we have here. Now if we do breadth first, starting at 0, let's say, not at 2 but at 0. So who are the neighbors of, so let's just see the difference between depth first and breadth first here. So who are the neighbors of 0? The neighbors of 0 are 1. So in the adjacency list of 0, there will be 1 and 2. So now in breadth first, I take this and go deeper. Now I'm not going to do that. I'm going to traverse this and then proceed. So first time I look at 1, 2. Now I look at 1. Now who are the neighbors? And 0 is marked as visited. So I look at 1. 1 has a neighbor who is 2. So from 1 I go to 2. And 2 has, now I go from 1 to 2. So 2 is there. Now as I have put it in the queue, I have already marked it as visited. So 1 is visited and 2 is also visited because already there. So so what I do is I go to 0, pick up the neighbors and add them to the queue. So my queue consists of 1 and 2, and I mark 1 and 2 as visited. So at this moment 0 is visited, 1 and 2, because they have been added to the queue, they are also visited. So now I pick up 1, so 1 is gone from the queue, it's a queue. So it's a first in, first out. So I go at 1, and 1 has what neighbors? 1 has only one neighbor, 2, which is already visited, so there is nothing to add. So that's it. So 0 gets displayed first, then 1 gets displayed. Then I go to 2, so 2 gets displayed. So 2's, who are the neighbors of 2 which are not visited? 2 has 0 as its neighbor and 3 as its neighbor. Okay, sorry, 3 as its neighbor, because 2 to 3. So 3 gets added to the queue, okay, and 2 gets printed. So 2 is done, because 2 has only 2 neighbors, 3 and 1. Not 1, sorry, 0, which is already visited. So 0 is out. So we have only now 3 in the queue. So now if I do 3, what will happen? So 3 has only one neighbor, 3, that is from 3 you can go only to 3. So we pick up 3, we mark 3, and then because 3 is already visited, we don't continue, it's already visited. So that's the end of the story. So this will be, I guess, 0, 1, 2, 3, or 0, 2, 1, 3, because both the neighbors I can visit them in either order. Only thing is, you have to remember that here, okay, now let's see if I get a different answer if I do DFS. Okay, this is Bfs. Okay, in DFS how it will go? 0, neighbors of 0 are 1 and 2. Yeah. Okay, 1 and 2. So let's say I go to 1 first. So the neighbors of this are 2 and 1. So I take 1, pop 1, and now once neighbor is 2. So I have seen 0 on the screen, then 1 on the screen. Then 2 is already marked as visited, so there is no question of going to 2. Whenever I add it to the stack, just like I add it to the queue, these are marked as visited already. So here I then pop 2. It's too small a graph to have much variety. So I pop 2 and find out for 0 and 1 the only neighbor is 2. 2 is already visited, so there is no question of adding it again. So it comes same, 0, 1, and now if I do pop 2 and find out who are the neighbors of 2, I get 3. So 3 gets pushed onto the stack, and then because 3 is the only guy left, he gets popped. So it will come in the same order. I guess the Bfs traversal and the DFS traversal starting at 0 will come at in the same sequence. Or of course you can always visit the neighbors in the reverse order, but I tried to take the same order, so it came the same. Maybe the answer will change if you do 2. But the important thing to remember is, in a Bfs, I look at my neighbors first before looking at their neighbors. Okay. So I will, okay. So maybe I will try and explain that with a different. So suppose I had something like this: 1, 2, 1, 3, 2, 4. Okay, maybe with just this it may make a little more sense. So this is 0. So if I start DFS at 0, and as you know we use a stack, so I go to 0, mark it as visited, look at 0's neighbors 1 and 2. So if 1 and 2 are the neighbors of 0, then in the stack I add 1 and 2. Now let's try to do with Bfs with 0. Again the neighbors of 1 and 2, but then I add them in a queue. So I have 1 and 2 in the queue. Okay. Okay, now, okay, to retain that order, let me make it 2 and then make it 1. So BFS I do 1 and 2 because I can visit my neighbors in any order in any case. Now I pick up 1. In DFS, I'll pick up 1 and of course 1 is marked as visited and it's displayed. So my stack now will look like in DFS, it will look like I'll pick up 1's neighbor, which is 3, and put 2 stays as it is, okay, here. And then what I'll do, I'll pop 3, okay. I'll pop 3, so I'll get 3 here, because I'm going depth first, okay. So I'll have 3, then I'll go to 2, so my stack will look at 2 now. I'll pop 2, so I'll say 2. Who is 2's neighbor? 4. So 4 will come. Sit on the stack. Now there's nothing in the 4, so 4 will get displayed. Okay, so this is how the output for DFS will look. This is DFS. Okay. Now let's start BFS again at the same point, which is 0. So these 2 guys will be added to the queue, 1 and 2. These will be added to the queue. Now when I add these 2 guys to the queue, I'll pick up 1 and find out who is 1's neighbor, and of course in the output I'll see 0, I'll see 1 because I have popped 1, then I'll pick up 1's neighbor and add it behind, not at the top, right? Here see at the top, I added it at the top of the stack because it was depth first, I went like this. So 0, 1, now I'll get 2, then I'll mark 2, 2's neighbor is 4, okay, so I'll add 4. Then I'll get 0, 1, 2, I'll get 3 and 4. Okay. So I think if we draw this, okay, you will get a different order for a BFS and a different order for a DFS. DFS goes depth first and then it chases this guy. Once this depth has been chased, so BFS would go this way, not this way, it would go 0, it would visit its neighbors first, see that, 1 and 2 will come first, then it will come 3, 4. So it's like a level order traversal. I am drawing a very simple graph, so it will come in that order, okay. So for certain problems when you want to go horizontal, then BFS is a good data structure. The only difference is instead of using a stack, we employ a queue. Okay. So that is the only difference. Rest of the code entirely remains the same. So what I guess we can do is we can run this algorithm. You look at, I've just given you a brief idea of BFS. So just look at the Bfs code and then we will talk. Okay, so we'll open up the Bfs code, mute. displayed on the screen? Yes. Yeah, please look at this code and you'll understand how Bfs works. Okay, since I don't want to spend too much time, let's walk through this. Okay, so you have a class graph, you have all the standard list and all. This is your adjacency list. Okay, this is your adjacency list. Okay, let me use the highlighter for a change. So this is the adjacency list. Then we have the add edge function, we have the BFS, and then we have the constructor for the graph. Okay, so if you can go down, okay, let's erase this. Okay, so as usual, can you scroll up? Just get the line 19. No, go. Line 19, let it be top. 19. No. Okay, so we can't get it in one shot, but it's okay. So we have graph int v. This is the number of vertices, so it initializes and creates a adjacency list of v vertices, because each element in the vertex will be a list of integers which are the neighbors of that vertex. Correct? This is how the adjacency list looks. Okay. Now we have the graph add edge. So it goes to that, if there is an edge from v to w, it goes to the slot v in the adjacency list and adds to that slot, where it will find a list. To that list it will add a w as a vertex through which w is connected, v is connected. Okay. So add w to v's list. Now let's look at the Bfs algorithm itself. Let's scroll up. It should not be too complicated to look at the Bfs algorithm. Now scroll up, such that Bfs is at the top. I think that's enough. Okay, let's quickly go through this algorithm. So we have graph Bfs int s. So this is the starting point of the Bfs traversal. We create as usual a Boolean array of v vertices. Initially all are marked as unvisited, so visited is false, all the vertices. Then we say list of int. Now he's creating a queue as a list. Doesn't matter how you use the list, will decide whether you can use it as a queue or a stack. So he's just using a list, and he'll use this function pushback and front and pop front. So that will make it use as a queue. So queue is simply a first in first out data structure. So list of int q. So you will mark the first starting vertex as visited, yes, and then he'll say q back q. Once he marks it as visited, then only he pushes it back into the queue. So the queue will now contain the starting vertex, and then he will start. He'll create an iterator which can go through a list of integers like we did earlier. We'll need this iterator to go through all the neighbors of a given vertex. So while not q is empty, as long as there are some elements in the queue, while q is not empty, then we say s is equal to q dot front. Okay, s is q dot front. So we get the first element from the queue. We display it now. So far we have marked it as visited, but we have not displayed it. So at this point we display the element which is coming from the queue front. So this just shows the element, but this gets rid of the element. So this is like the pop. This is like the top. For a stack we have the top and the pop. Here we have the front and the removal. So this will delete that element from the queue. Then so we have got one element. Now what do we do? With that element we again go back to the adjacency list. We begin and we go up to the end. And now what do? We see if a particular vertex has not been visited, which is a neighbor. This is looking at the neighbors of S. So we are going to go through the list of neighbors which are there in the adjacency list. So ADGS S is a list, remember? On a list we can do a begin and we can go up to end and plus plus. So if any of the element is not visited, if not visited, star of I. That is, if any of the neighbor is not visited, we mark him as visited. then push him back in the queue. And then we'll pop him at a later date. So all the neighbors, so given any edge, given any vertex, sorry, we will look at all the neighbors of those vertices, there may be more. All these neighbors of this vertex will be pushed one by one into the queue. And so if this guy has some more neighbors, they will be visited later, not like a stack where we visit them first and then go for them. So in a DFS, we would go here and then go here, and then we would look at the neighbor of the earlier guy. Now it won't happen like that because we are using a queue. So these two guys will be at the back of the queue. Okay. So the queue will initially consist of these three guys, and they will, each guy, when he sees some neighbors, he will be printed, and his neighbors other than these guys, these are already marked as visited before they were put in the queue. These guys will be now added here. So first the root node's neighbors will be visited, then their children will be visited. So if this guy has children, so let's say this is 4, 5 and 6. So then 4, 5 will come. Then this is 1, 2, 3, let's say. Then 6 will be added. When 2 is visited, 6 will be added. So 6 will come. But we will not visit 4 and 5 before we finish 3, because 3 is already in the queue because of neighbors of 0. 0's neighbors are 1, 2, 3. They were all added to the queue. So the queue will go first 1, 2, 3. Then while going through 1, it would have processed 4 and 5. It would add it to the queue at the end. While processing 2, it would have added 6. It would go there. But the order will be 1, 2, 3, 0, 1, 2, 3, 4, 5 and 6. So it will go in that order. Because the neighbors are not immediately visited, the neighbors are added to the queue. In DFS, once we hit a neighbor, we go deeper. Okay, that's why it's called depth first. Here, this is why it's called breadth first. We go first neighbors, we just collect who are the neighbors, keep them. But the order we will visit them is we'll first visit the first level neighbors, then we'll visit these guys. So without visiting these guys, these guys will not be visited. Okay, so this is first. This is first, then this comes, and then this comes. Okay, so the order will be maintained. Order of level. Okay, so if the graph is if like a tree, this leveling will be maintained using this whole adjacency list and queue. The difference is coming because of the queue data structure. Okay, so that is why it is coming. Okay, so I think. That is straightforward. I don't think this deserves more time. And BFS and DFS both, you have to become extremely friendly because we'll use these algorithms a lot in our actual coding work which we will do. Okay, so we'll use them quite a bit. Okay, so having I don't know how much of, now do you understand BFS and DFS? At least to a large extent. You can run that code if you want and check how the order is. Okay. So if we are done with that, we can move on because there is one important area that I want to cover. Okay. That is how to access MongoDB in Flask. Okay. Now I think are you familiar with MongoDB a little bit? Because we are going to do that, and I am going to show you a quick demo.
So we need to switch assist.
Acha, we will need a little. Acha, before that, I just want to check how many of you know MongoDB. Because then we can give you a. No, we are not using SQL. We are using MongoDB.